polarity and intermolecular forces. All right, so we talked briefly on this when we talked about water and how it expands as a solid, and that's why it floats to the surface, and that's why the rivers and oceans freeze top to bottom. And so when we look at polarity, what it's essentially telling us is there's an uneven distribution of charge if something's polar. So polarity refers to the tendency of that molecule to act kind of like a magnet. Due to that arrangement of atoms and it not being symmetrical, all right, you have more charge on one side than the other. One side has more electrons than the other. So for example, down here at the bottom, we see HF. And so we know that fluorine has those 3 lone pairs around it. Look at all of that negativity that surrounds fluorine, but then hydrogen is just by itself, right? And so you see that uneven distribution of charge. Therefore, because of all of those electrons, fluorine is partially negative and hydrogen is partially positive. Think of it as a tug of war between those molecules. All right, and so when we talked about covalent bonds, we talked about how they could potentially be polar and non-polar. We didn't go into a lot of detail about it yet, but we said, hey, this is possible. It can be polar, meaning it's evenly spread. All of our electrons are evenly distributed throughout the molecule. Or it could be polar, meaning that they're not equally distributed. There's a dipole, all right? Dipole means an uneven distribution of charge. And there's an atom that is significantly higher electronegativity than the other atom. So imagine it as like a tug of war. Fluorine is the big bodybuilder and hydrogen is just a normal little person, right? And so fluorine is winning that tug of war between those electrons. So if those are your electrons, fluorine takes this one on the left and has a greater pull towards itself. All right, and so fluorine becomes partially negative. And so that arrow represents that uneven distribution of charge. And your atom that is more electronegative, remember, that's how tightly they're holding their electrons. Therefore, the one that is electronegative is going to have a greater pull on that electron. All right, and that's what causes it to be partially negative. And then hydrogen, partially positive. Any diatomic atom. If hydrogen is bonded to hydrogen, diatomic, di means how many? 2, diatomic, 2 atoms that are the same. So hydrogen to hydrogen. If we put 2 of the same things in tug of war together, is anybody going to win? No, it's a dead tie, right? So there's an equal pull on these electrons in that bond in between. So non-polar. If I were to look at chlorine bonded to chlorine, we have all these lone pair of electrons surrounding it. But is there an even distribution?
Oh, yeah, that is.
Yes. All right. So we see both chlorines are equally as strong, equally as negative, and so it's an even distribution, non-polar. But polar means we have 2 opposite ends. So if I look at nitrogen, NH3, and what do we have at the top of that nitrogen? Anybody remember what it looked like?
2 dots.
2 dots. Here's this big zone in that cloud, your little ghost, of what? What are those 2 dots?
Valence electron.
Electrons, which have what charge?
Negative.
Negative. All this little squiggly sign means is partially. So this side is partially positive or partially negative. Therefore, is there an even distribution of charge in this atom? No. All right. Your top part is going to be more negative than everything down here that's balanced out. So you have an uneven distribution.
So that would make it a polar covalent bond.
Correct. That would be polar. All right, let's take a look at another example. If I had CH4, is that carbon pulled equally?
Yes.
Yes. All right, what if I change 2 of these hydrogens? Remember, these are 3D, right? What shape is this?
Tetrahedral.
Yes, tetrahedral. All right, so let's say I replace 2 of those with chlorines.
Still even.
Is it?
Indeed.
Yeah.
It's not actually, because the chlorines have two terms.
I mean, the carbon.
So the hydrogen. No, the hydrogen can't have it.
That's not.
Yeah,
Hydrogen doesn't have any.
Yeah, because aren't those invisible or something like that?
It's no hydrogen.
They're
It's
still
even. It's equal.
impacting.
It's balanced.
So let's take a look at this. Based on your Lewis structure, it looks even, right? But
They're not.
what does it actually look like? Let's look at it 3D.
Hey, try it.
All right. Here's what you have, right? Let's pretend these two atoms right here that I'm touching. Those of you online that can't see what I'm touching, it's the top and the bottom. Those two are chlorines. All right. Let's turn it this way and look at it. Chlorine, chlorine. Because it's three-dimensional, look, when they were top and bottom, it looked like it was all balanced, but are they actually? Look at all of these zones of negativity on these attachments, and then these are just plain hydrogens.
Oh, so it pushed the hydrogen.
So no.
Right, the hydrogens get pushed down more, polar and non-polar now. Polar. All right, so that's why your dimensions and your shapes are so important, because if you don't know that three-dimensional shape, do you see how these are going to be projected? All right, and so we need to be able to recognize the shape to know whether or not they're actually evenly placed. All right, if you were to have drawn the Lewis structure like this, you would have easily seen that it was polar, right? Because you'd see that overload on this side. However, some of you may draw your Lewis structure other ways, and I see that mistake all the time on tests. It's something like this, and you've drawn it with the chlorines on the top and bottom, and you say, oh, it's non-polar because one's on the top and one's on the bottom. Not thinking about it three-dimensionally, that they're actually sticking out of your paper, and so that negativity is on one side. And so looking at what does this mean for substances as we put them together? Well, we use the term like dissolves like. Polar will dissolve polar. That's why sugar dissolves in tea, because sugar molecules are polar and water molecules are polar. That's why we can dissolve salt in water, right? Water's polar, salt, Na plus, Cl minus, all right? And then non-polar substances dissolve other non-polar substances. So why do you think oil and water don't mix?
Because they're non-polar. Because oil is non-polar and water is non-polar.
Yes, because oil is non-polar and water is polar. All right, so that's why oil and water won't mix. Or in this dressing, the oil and vinegar. Or even you see a puddle, right, in the parking lot, and you'll see the film of like a little rainbow and oil on the top. That's why that's sitting on the top of that puddle, because it can't mix with water. So think of it as you've got these magnets in a bag, all right? And then I'm going to come in, I'm going to throw some rubber bands in the bag. Here's my rubber bands. All right? And I'm going to shake the bag up. What happens? What happens? I've got magnets and rubber bands. The magnets stick together and all attract to each other. All right? And the rubber bands are just kind of free flowing. Right? They don't have anything to stick to each other. And so that's why they can't get in here in between all of that attraction. All right? They can't get in between the molecules that are stuck together. So they just kind of float wherever. That's why polar substances or non-polar can dissolve in non-polar. So if you were to mix two oils, they're going to mix, because it would just be like mixing different color rubber bands in, right? None of them are attracted to each other, so they can just mix in everywhere. Here's another rubber band, the green ones. All right, they're all going to mix in because there's no polarity that's keeping them out. And so that polarity leads us to the forces between the molecules. It's what holds water together. Why water is a puddle. That's why water is a liquid at the temperature that it is. So intramolecular forces are between the atoms. So if I were to draw water, All right, those green lines, those green bonds are your intramolecular bonds. All right, if I had another water molecule over here, again, there's your intramolecular bond. Inter refers to here's that partially positive, here's that partially negative, and these two are attracted to each other. All right, and so that is your intermolecular forces, attractive forces between molecules. All right, these are between molecules, these are in molecules. Right, so that's what we're going to talk about. This is water, and hydrogen bonding that we said causes water to expand when frozen. So the hydrogen bonding that you see take place in water is because water is a polar molecule. It is one of the strongest intermolecular forces, hydrogen bonding. That's why water's boiling point is so high. All right, that's why water is a liquid at room temperature, because you have these forces that are holding your two molecules together, preventing them from spreading out, right? And then when you heat them, we know that heat is really just what? Starts with an E.
Oh,
Energy, yes, good job, Brady. It is just energy. So as we apply energy to these molecules, they start to break that bond and weaken it as they move away. And that's what allows it to spread out into a gas. And so if you have a polar molecule like water, and you see a hydrogen bonded to a nitrogen, oxygen, or fluorine, all right, has to be one of those three, then you have hydrogen bonding. If you have a polar molecule, but you don't see it bonded to one of those three, then you have dipole-dipole. That's simply all the rest of your polar molecules that don't have F, O, or N bonds. We call it a Fon bond. If you don't see a Fon bond, then it is not hydrogen bonding. It's dipole-dipole. Everything else would go into the dipole-dipole category. And then if you have something that's non-polar, the only option is your London dispersion. It's the weakest, all right? Think about it. The air we breathe, oxygen that our lungs require, is non-polar, right? What allows it to be a gas at room temperature? The London dispersion forces. It says dispersion, another name for it is London dispersion. All right, so because it's non-polar, it has very weak, little to no force between them. All right, so it is the weakest of the intermolecular forces, and therefore oxygen molecules can spread out into gases. All right, methane, CH4, is able to spread out in the air as a gas because its intermolecular forces are very weak. All right, and after we find the polarity, you get to your lovely little intermolecular forces. So if you determine the molecule's polar, you have two options. So you need to ask yourself, is there a Fon bond? H to F, H to O, or H to N? If there is, what is it? Hydrogen bonding. If you answer that question no, what is it? Dipole-dipole. All right, and if it's just simply non-polar, what's your only option? London dispersion. You may call it dispersion for short. You may say LD if you want. All right, London dispersion. All right, so let's take a look at some of these examples up here. You cannot do this without drawing your structure. All right, we're going to mark out number 5. So CH3CF3, carbon bonded to a carbon. Are y'all good? Do y'all understand the structure of it at least? Yeah. Are we good to here?
Yes.
All right. And we know that your fluorines have lone pairs. Yes?
Yes.
All right.
Yeah.
Carbon plus fluorine, 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 hydrogen, hydrogen, hydrogen. All right. And so what are these lone pairs? Electrons. What charge are electrons?
Negative.
Negative. All right. So you have all of these clouds of negativity surrounding your fluorines. Yes. So imagine these are like big gray clouds around it. But then here is atoms. Atoms have what? Protons, right? And their electron is here attached to carbon.
So it means it's polar.
Yes. Look at this even distribution. Does any atom have more electrons than the other?
Not little bit.
Does any atom have more electrons than the other? No. So what would this be? Is-
Non-polar.
Non-polar. Meaning not opposite sides. They're all even. Non-polar means it's even.
I get it.
If I replace this hydrogen, let's replace it with a fluorine.
That's polar. It's polar.
It's polar. Why?
Because
It's positive and negative because north and south. Wait, no.
Poles.
Yeah.
North and south poles are opposite.
Yeah.
Yes. So see all that negativity surrounding it.
Yes.
Do we see that?
Yes.
All right. So look at NH3. Polar or non-polar? Have all these atoms bonded, but what's up here?
Lone pair.
Lone pair, your little ghost. So here's this big region of negativity surrounding that atom.
Polar.
Yeah.
Polar.
Yeah.
Yes.
So would it be
Yeah, Laura.
hydrogen?
Yes, hydrogen bonding. 'Cause that was
H was connected or whatever.
correct.
Wait, so they've all been polar so far, right?
Good job.
They've all been polar so far. Right?
Except for CH4, yes. Here's your hydrogens, and then you have that lone pair up top. Whenever you see a lone pair on the central atom, it's automatically polar. Just because you don't see it, though, does not mean it's non-polar. That's where we saw it CH4 compared to CH3Cl. All right, let's look at H2O. Your Lewis structure has 8 electrons. All right,
Non-polar.
no.
Polar.
Look at,
Oh, it's a positive and then 2 negatives. And it's on the central atom, so it's automatically.
yes, they're on the central atom, so it's automatically polar. Good job.
Go you.
So let's take a look at this. For those of you who are like, but wait, one's on the top, one's on the bottom, why is that not evenly distributed? All right, because somebody in here is thinking it. I know it.
Wait, what do you?
All right, when we looked at the Lewis structure of water, this, imagine this is flat, is what we see. And so you go, well, there's top and bottom and side to side. But is this evenly distributed? Look at the 3D molecule. Can I put all of my negativity on one side?
Oh,
yes. All of my negative, look at this cloud of negativity that I've gotten as a result of turning it. Last one. CO2. Polar or non-polar?
Not polar. No, not polar. Yeah.
Non-polar, why?
Because it's
Because they're
distributed
equal.
on both sides.
Yeah, they're equal.
Yes,
Yeah.
correct. Good job.
Yeah.
Evenly distributed, however, that doesn't always mean it's not polar, right? Because, oh dear, remember we had this. H, but we had a chlorine here. There's no lone pair on the middle, but is this polar?
It's polar,
No,
guys,
it's
because
not.
it's not.
It's
Hey,
not
look,
the
it's
same
a cloud.
size.
It's a
Look at the big
It's a
cloud of electrons.
Yeah.
Yeah,
I'm in polar.
I'm
Good job, Lauren. It's all right.
So that's what I'm saying. Just because they're not there doesn't mean that it's non-polar. All right, but every time you see them, they're polar. All right, so look, this big cloud. There's a big cloud right here.